I must say there's a slightly more of you than I expected. So clearly the food works. Right, let's carefully begin. So where should we begin? So I was thinking, should we begin with theory? Yeah. But perhaps maths at a time lunch is not ideal. So I was thinking, perhaps as the good Singaporean obeying citizen, I shall start with textbook, because textbooks are always right. So what does textbook tell us about thermal quantum sensing? Right, in any quantum optics textbook you may pick up, say by Loudon or Mark Fox in this case, sooner or later, probably sooner, there'll be some mention of photon statistics. But instead of delving into equations, let's have a very quick sense, just an idea, what does that even mean? And digest that in a minute. So if we can see photons, like little dots or particles of light, what would they tend to look like? Say if we are to see the photons from this room with our eye or our APDs, what kind of timing distribution would this be? Well, it probably maybe looks something like those red dots. Specifically, they will follow Poissonian distribution, a random distribution, whether for uncorrelated light source, what we may call ambient light, or coherent laser light. A second class of features, if you will, or timing distribution would be anti-bunching. So they will tend to avoid each other. Say if you have a single photon, one click at a time, well, then it makes sense if you see one, there shouldn't be a second one in some time constant. The third one is what we're interested in today, photon bunching, the tendency of photons to propagate closer together than random statistics, as given by the imagination, that little clustering over there. If we are to measure this, what would this manifest as? It will manifest as photon bunching or some form of peak. But what plot is this even to begin with? What is this G2 plot that can tell us, yes, this is photon bunching. Yes, this may be thermal light. Well, what is G2 in a very fast way? So thermal photon bunching, how can we measure? According to a textbook, straightforward. Have a light source, have a beam splitter, split the path into two, have any two detectors of your choice, and you measure a correlation. And according to SIG textbooks, the result is again straightforward. It will be this. If you measure laser light, the G2 you measure will be flat. No bias, no preference in any timing delay. But if you see a thermal light, well, there will be this bunching peak that goes up to 2. But although this is the case, I predicted in the 1950s or 60s, but for the better half, well, not better half, more than half a century, this was not actually observed. Why? Because if you think thermal light, if you have to think of thermal light right now and ask you to find one, what would it be? Well, for myself, naively, I'll think of, say, fire, heat, candlelight, sunlight. Those would feel obvious to me. But all these light sources will have a common issue, is that they are black body radiation. They are continuous spectrum, at least in the visible range, that makes it hundreds of nanometers wide. And if these light sources are hundreds of nanometers wide, this bunching, this tendency of the photons to propagate closer together will be exceedingly small, well, given by the Fourier transform of the spectrum. As a time scale, it means femtoseconds. And right now, we don't have detectors that can measure femtoseconds. What do we have? Nanoseconds, typically, for say, a passively quenched APDs. Nanowires maybe go up to tens of picoseconds. So given that reality, we don't actually measure this. What do we measure will be this, which looks slightly different. So how do the textbook explain this? So if we delve a bit deeper, when the textbook gives you the ideal case of thermal photon bunching, and they present you the plot, there's a caveat. They say pseudo-thermal bunching, pseudo-thermal light. And then for the next few decades, the light sources they use invariably will be laser light through rotating ground glass, laser light through microspheres. And when people do try red body light, for example, HPD themselves, the G2 is on the 5th or 6th decimal place. And if you hunt down the literature and you see what HPD did, they did measure the starlight. It took them 12 years. So not wise for a PhD student. So is there any way out? What can we do about this? So it turns out there is a side trick we may explore. This could be a thermal light source. Cannot see, right? Yeah, so we expand a little bit. And just for those of you at the back, just in case. So this is a laser diode, not the normal side. Normally is this. If you take a laser diode, you can actually generate thermal light. At this point, you may feel, laser diode should produce laser light. Yeah, literally. So is this a scam? Hopefully not. Why? So if you take a laser diode, it does not always generate laser light. It depends how much current you give it. So for example, in this plot on the horizontal scale, is the current you go a diode from 0 to say 60 milliampere. Let's look at the upper plot. The upper plot is the output power of that diode. In this case, it is a logarithmic plot. If you increase this injection current, if you will, beyond a certain point, this dash light in the middle, yes, it will start to laze. But if you reduce it, at some point, don't stare at it, the light will dim. And that's when it starts to behave more like an LED. The intensity will sharply drop from milliwatts, drops to microwatts, and the spectrum, instead of a single emission line, will escalate into something like tens of nanometers. So this is above threshold, you get laser light, and sub-threshold, you get a more LED light with perhaps thermal statistics. Where do we want to be? Well, we want to sit right at the middle, near this threshold, where this light is narrow band like a laser light, very bright, but thermal. If we can do this, what will we do it for? Well, then here comes the important question, which takes perhaps many of us now, which is, where is the money? I mean, where is the synergies with our value partners to identify key quantum enablers and things? So, or in Singlish, got what use? Why do we even bother with this? Let's hold this light source for a moment. Is there something that we can attach to? Is there a problem? Well, roughly Googling, just for a very naive sense, it seems there are some applications, or at least some questions in industry. In this case, in the automotive industry, specifically autonomous vehicles. In their line of literature, it seems the problem of crosstalk is still quite prevalent. The obvious problems of that, whether it leads to accidents or hacking or all those, I leave it to them. But I just want to quickly touch, what does crosstalk even suggest? So, in autonomous vehicles, imagine you have two vehicles, A and B. It shines some laser light from vehicle A in this red pole, and your vehicle B shining another laser light. You can imagine there's a non-zero chance that these two vehicles might somehow shine at each other. Well, fine. So they have two laser lights that overlap. Why does overlap in beams mean crosstalk? Where does this crosstalk come from? Well, it's because this laser light have to be modulated. In this very simple illustration, modulated in time, just pulsing it up. So here's the issue. If you are, say, vehicle A, and you pulse light at some modulation frequency at B, and B accidentally or intentionally pulse at the same modulation pattern, well, the detectors, they confuse these two, and you can't tell the difference. And that's where crosstalk may appear. Holding this very naive interpretation, a natural question I suggest to your consideration is, can we do this correlation without modulating the light? A light that is unmodulated, can it carry correlation information? Yes, and that's the thermal light we have. So if we then look into literature and we search for words like, say, quantum illumination, quantum LiDAR, And you'll see that in the past 10, 20 years, there have been many suggestions using SPDC light, spontaneous parametric down converter light. Many seems to suggest entanglement. But in whatever proof of concept there is, almost all of them use only the correlation property of that SPDC light. Holding that from a naive experimentalist, how bright are these light sources to begin with? So in this plot of say photon counts per second versus a spectral wave, it seems that SPDC light source in the literature, and please just shoot me or correct me if I'm wrong, the brightest SPDC light tends to be millions of counts per second, tens of millions of counts per second, not too much more. And that's it. That's tens of millions count. It's bright in the laboratory. It will saturate most of our detectors, but that's sub-picowatts. This laser pointer is milliwatts. So sending a sub-picowatt light across a surface, reflect over a distance, is slightly difficult. Therefore, question is there any light source that is a touch brighter? And that is where we are. So we have a light source that sits somewhere here. So in terms of spectral density, about 10 orders brighter. So why does it need to be bright and narrow? Is so that you see this bunching signal at all. If you look at absolute intensity, you will notice there are other light sources in the top right. Erbium doped fiber amplifier, superluminescent diode, and frankly, the sun. But all these, although they are bright, they are also either multi-mode, multi-spatial mode, or very broadband. Therefore, not actually measurable G2. To have something narrow and bright, this is where we sit. So, let's demonstrate. Can we show it in a ranging measurement, perhaps a distance measurement? But what would be convincing with just a single plot or perhaps a photo? A breadboard measurement may not be convincing if I'm going to say, hey, this is useful, and then I show something 5 cm. A room, perhaps, demonstrate across the lab, or perhaps down the corridor. So we went for something a bit more dramatic. I'll explain in a while. My bad. Yes, quickly go through the experimental setup. Maybe boring, maybe useful. So quickly go through the scheme. So we start with a laser diode, operate below the threshold to get the thermal statistics. We spectral filter it. E in this case is just an epsilon or a ferroball cavity. So effectively, it's just a piece of glass. We have refractive coatings on both sides. And BP is not an oil company, it's a bandpass. So effectively, this stage is to fish out one single emission line from the subthreshold laser. BS is beam splitter. So some of the light is kept as a local reference. The rest of the light, the majority, is sent out through a telescope. The spatial filter is to constrain a solid angle so that you pick up only your target and not like everyone and everywhere all at once. And then whatever light that returns back, you measure the correlation between that return signal and the local reference just now. This is your G2 or correlation. And this was the hinted slightly dramatic place. So this was measured from the Marina Bay. Not because we wanted to stay at a nice hotel. There's actually a reason, if you can indulge me for a moment. This distance is about 2 kilometers. If I ask you now to measure something, line of sight 2 kilometers in Singapore, where will you go? We are not exactly a low population density place. And if you look at the map, places with low density is called army base. I don't want to be there. The long straight path of road, yeah, is for airstrip. I also don't want to be there. So there is a road in Changi, but on the left is the airport, on the right is the airbase, at the front is the Navy base. I don't think I want to be there. As security guard, hello, perimeter difference. I don't want that. Is there anywhere else? Kilometer range. Well, if I stare at the map long enough, there was too many recce's. There's one more place in the west. It's called Lim Chu Kang. Not a place you want to be alone at night in the rain. For those of you who don't know, Lim Chu Kang is the cemetery. So Given all that constraints, what else do we need? We need the equipment probably in a place with electricity, preferably with some form of roof, because when the rain comes and goes, I don't want like everything to short circuit. I want a clear line of sight. Don't want people to like walk in between. So we end up here really. So because the other consideration we had was, what if we went building to building, like find two friends of soon to be former friends in HDB units and look at each other? But that would be risky, isn't it? If you look at each other and someone see, hey, there's a telescope there. Yeah, I don't want to complain. So we ended up here, we set up the LiDAR equipment here, and the signal was sent out to somewhere over here. So, and over here was, I think, some people from the group who had to stand in the rain and not complain too much. I just off the phone. Anyway, so another advantage of doing this was the disadvantage. This light, the LiDAR signal, if you will, have to go over the Marina Bay, which actually presents some problem because of all the evaporation and turbulence. I mean, you walk down the road, you look by eye, you see all this like turbulence. So this affects the mode coupling quite badly, and we lost maybe 6-7 orders of light. I didn't optimize it. But even then, on a rainy day, we still managed to see a relatively clean signal, which is in a way not unexpected because it's a G2 measurement, which is phase independent. So even if it rains, it may affect the signal to noise, but it won't introduce any spurious signals. So as of this plot, say 1 kilometer, because we aim at different distance, and then I'll tell them, hey, go away, go somewhere far. Yeah. So, and a 2 kilometer distance. So this is just a very simple, oversimple demonstration, if you will, of what we can do with a relatively simple resource, a subthreshold laser diode. If I still have your attention for a while here, I will now take a slightly more blue sky sidetrack. By blue sky, I mean something that will have no return on investments to the economy and therefore no grants. But I do it anyway. So on this plot, other than this light source as a thermal light, where would the most prevalent thermal light we see be on this plot? Where would the sunlight be? So sunlight, if you don't filter it, is of course out of the screen. But if you filter it to say picometer light wave, it will sit somewhere here, 10 orders of magnitude dimmer than the subthreshold laser light. That's very low. But can we still see anything from it? Let's give it a try. This is the setup, almost identical to just now. Quickly go through. So coupling sunlight. In this case, this measurement of sunlight actually is you go out that door, turn right, turn left on that bridge. That's it. That's where the measurement took place. The telescope was 1 X-ray lens. The aiming was, not very high-tech, not quantum tech. A single mode fiber, because, well, the sun is large. It is a extended light source, so we have to pick up a single spatial mode for spatial coherence. The filtering stage. This is spectral filtering, a bit more complicated than just now because sunlight is broader. So in this case, a few interference bandpass filters, 2 echelons of different thickness. Why different thickness? If you can imagine, say, a comb, say a comb of some spacing and a second comb of slightly different spacing, and you overlap them, the effective separation would be like a lowest common multiple, if you will. So by stacking 2 echelons of different free spectral range, you get something that is a few nanometers FSR, and that works with the bandpass. Effectively, what this does is you have a light source that's a few 100 nanometers wide. You filter, suppress everything, except one line that is about picometer wide. Use it. We pass it through a Kian Taylor, effectively just a broadband polarizer, if you will. Motivation is because orthogonal polarizations don't interfere. This is just to double the bunching effect. PBS, again, just to split the light into 2 detectors, and we measure our G2. What do we see? According to our friendly textbook, by right, this is what they promise. And indeed, this is what we see. Close enough, I hope. So we were probably amongst the first to see this from sunlight. What then? Can we push a bit further? So now that we can see this photon bunching effect from starlight, then it attracts some attention in the astronomy community outside Singapore, because I don't think there's an astro community here or in a 1,000 km radius. Anyway, yeah, so stellar photon bunching. Is there a way to measure these quantum correlations of light from the stars and open up perhaps a new probe or just a new measurement scheme? Well, so we take that measurement scheme or instrumentation, we make it 3D. Okay, I know. We make it compact so that it survives the trip to the US and not scattered into 5 sub-equipment. And we mount it on a telescope. So this red tube is the, I don't know, this is the size of a room. It's a 1 meter kind of a diameter thing. And we mount it at the prime focus. And we try to measure some starlight, Sirius, Vega, Arcturus, whatever is brightest now. Unfortunately, oh yeah, so this we will be going again in a few weeks' time, which reminds me we need the setup to maybe work first. Hint. Yeah, just to share, that's what the telescope looks like. Red light because astronomers is just to help the eyes adjust to the dark. And yeah, you can tell I like astronomy, right? Yeah, it's a different vibes, you know, when you do something not for KPIs. Because, you know, anyway, the last attempt looked like this. Yeah, so that's reality of science. Ooh. Training your patience, I think. So a quick overview before we finish our lunch. So thermal light or sensing with thermal light is not exactly mainstream today, kind of. But I'd like to share with you, it is maybe worth our attention, just a little bit. So where are we now? So we have some experience, I think, in generating thermal light here and there. For example, we play a bit with SPDC light. That is the work driven by He Zhong, who is now enjoying life, I think, in China. And by enjoying life, I mean he spends 90% of his time writing grants, 5% doing science. So we play a bit with SPDC light, maybe asymmetric wavelengths, so that we can see something visible, maybe something in the infrared where it's interesting. We play a bit with narrow band, such that we don't see dispersion in fibers. We play a bit with breakdown flash, work by Ho Soon, who may not be somewhere back. Breakdown flash is also a reason why we use PBS just now to suppress the optical crosstalk between the detectors. We're also now investigating what does it mean to be thermal light, or whenever a paper just hand wave and say pseudo-thermal light, chaotic light. Is there a difference? It turns out there is, and we will archive that soon. So we have some experience generating various flavors of thermal light. Whatever that seems to imply. We play a bit with detecting them in the spatial domain, in the temporal domain. In the temporal domain, we observe it from, say, arc lamps, let's see, mercury light, arc lamp, subthreshold laser diode, sunlight, starlight. Hopefully, the distance scales also increase from meters to maybe light years. We play a bit with dark field imaging. I think Zhen Xing is doing that to have some idea that some spatial information or maybe spatial correlation propagates. Can we assess that? We are now very nascent touching correlation spectroscopy. Visible, maybe infrared. We see how. And stellar interferometry is what we will do in 3 or 4 weeks' time. So if we have some experience generating thermal light, a little bit in detecting them, and we combine them, maybe this has some usefulness or use case. What application can there be? Well, as shown today, in terms of distance measurement or LiDAR, there seems to be some interest. And just to play safe, we patent it. I hope, but it won't be. We also can use it to synchronize clocks. plots that are separated, how do you synchronize it? Whether with SPDC or thermalite, work driven by Justin, Darren over there, hiding. We're also now beginning to look at photon statistics. Can we control this measurable G2? Possibly even encode information in it. Is there any advantage in terms of security, signal noise? I refrain from committing that claim at the moment. I save wavelengths because you don't want that bright LiDAR shining your eye all the time. So moving to telecom wavelength or beyond. And to wrap up, in case you're very bored, I accidentally help out in some science comics over the years. One for quantum physics for obvious reasons, and one on synthetic biology, which I really don't know how it happened. Of course, to wrap it up, all I did here is just stand around, talk a bit, and breathe oxygen. The actual work is, of course, done by mostly that quadrant of people hiding there, and I will end with their photos. For that, I thank you for your time and attention. Hi.